Okay. Oh my God. Oh. Very good. Okay, so Ryan is the first presenter this semester. He is in his third semester studying computer science. He's interested in data science and computer architecture, and he'll be presenting cores that don't count, which is an interesting paper focused on mercurial cores, which will be a new thing to most of you, I guess. Okay, you can go ahead, Ryan.
So welcome to my presentation about cores that don't count. This paper was presented at HotOS 2021. As for the presentation itself, first I will briefly summarize the paper. Then after the brief summary, I will get into the various different topics that the paper discusses. And then finally, I will provide a brief analysis, and then we'll get into the discussion. So for the summary, the problem the paper discusses is mercurial cores. Now, mercurial cores are, in essence, broken cores which produce execution errors. These execution errors can lead to significant losses in performance, so this is a major topic for hyperscalers such as Google and Facebook. The aim of the paper was primarily to raise awareness of these mercurial cores, as no prior research has really been done on these. On top of that, the idea was to serve as a call to action to both CPU manufacturers and hyperscalers. The paper details a variety of detection techniques to detect mercurial cores, as well as some mitigation methods that can be done to reduce the effects that these may have on real-life workloads. The paper finally concludes that mercurial cores are a major issue that is going to get continually worse as time progresses, and this is going to get worse without further research, and they still remain an open challenge. I would now like to provide a deeper insight into the problem at hand. At the time, processors were considered to be fail-stop, meaning that when something broke, they would stop working entirely. Or at the very least, they were considered fail-noisy, meaning that if something stopped working, if some issue came up, they would fail at a variety of different instructions, and you would realize something was wrong relatively quickly. However, the issue with mercurial cores is that they can fail at very specific instructions. So they can be fine for most types of instructions, but then produce errors for a certain specific type. As such, they're very difficult to detect, and also their effects can be very difficult to deal with. And this makes them much more challenging to do research on than compared to, say, conventional data errors. Here are some examples that the engineers at Google who wrote the paper encountered during their research. For one, they encountered a core which led to violation of lock semantics. This led to data corruption and various crashes in their programs. They also encountered a core which had broken encryption and decryption. This led to the fact that all the data that this core had encrypted could not be decrypted by any other cores, and only the core itself could decrypt the data it had encrypted. Furthermore, the authors encountered corruption affecting garbage collection, in which a mercurial core would prematurely trigger garbage collection routines, which led to live data being lost. Now that we understand the problem a little better, I would like to move on to some causes of mercurial cores. First, however, we should ask the question about whether mercurial cores are really a novel issue, to which the answer is most likely not. The authors speculate about a variety of reasons about why these have come up so recently. For one, this may simply be down to the fact that we have larger server fleets today, and as such, more servers mean more cores that have potential to break, or there's more potential for things to go wrong. On top of that, today we have much more attention to reliability. It's much more important for services to be reliable than it used to be. And finally, software has increased much, much more. So bugs that perhaps at a time were attributed to software, we now know are attributed to mercurial cores. However, the authors identified two major culprits, which they consider the most likely to be the reason why today mercurial cores are much more common than they used to be. For one, this is considerably smaller CMOS feature sizes. As we push ever closer to the boundaries of CMOS scaling, margins for error have diminished. And as such, the likelihood of something going wrong is much, much larger. The other reason is that nowadays CPUs are built in a much more complex way, and they perform much more specific tasks. So testing by manufacturers before they are shipped may not be rigorous enough to catch all the issues that CPUs may have. As for the concrete causes why cores become mercurial, we don't know. This is still mostly subject to ongoing research. However, what we can say for certain is that it is certainly a manufacturing defect. This is not like with, say, silent data errors, where the issue is something external, like, say, cosmic rays or alpha particles, but this really is an issue with the hardware itself. There's also the question about why mercurial cores become mercurial after lengths of time. Cores are not always mercurial once they're produced, but they start going wrong after several years of reliable use. The authors were also able to confirm a relationship between rates of corrupt execution errors and voltage, frequency, and temperature. However, they mentioned that it's inconclusive about how these actually affect the rates. Each of these factors had a noticeable influence. However, the impact would always vary. Sometimes it would affect it more, sometimes it would affect it less. So it's really unclear the causes are really unclear for mercurial cores. Since mercurial cores are a relatively new subject, the authors proposed some new metrics to measure both mercurial cores and the corrupt execution errors they produce. These metrics are purely hypothetical. They're not in use, but the authors speculate about them. For one, they suggest analyzing the fraction of cores that exhibit CEEs, or corrupt execution errors. They suggest looking at the age until onset, or how long it takes for a core to become mercurial. And finally, they propose looking at the rate and nature of application visible corruptions, or how often will CEEs affect real-life workloads. And when they occur, will they propagate through your program, or will they become invisible eventually? Now that we've looked at some of the causes for CEEs, I'd like to move on to how to detect them. Now, detection of CEEs is obviously essential to mitigating the effects. If you don't know that a mercurial core is there, you can't deal with it. The paper is primarily focused on software-based approaches, and it analyzes a variety of directions you may take when devising detection techniques. The paper also presents a variety of existing methods which they have to detect CEEs in mercurial cores. However, these so far have shown limited effects. There are 4 different directions you may take when designing the detection methods. And one such trade-off that the authors propose is automated screening versus human screening. Automated screening is the simple practice of searching for corrupt execution errors by an algorithm, whereas human screening obviously is doing the same, but manually by a human. The benefits of automated screening are relatively obvious. For one, automated screening is much cheaper and it's also much faster. However, it is considerably less reliable. Human screening, on the other hand, is much more reliable. The likelihood of false positives is considerably lower. And on top of that, human screening is essential to detecting new forms of CEEs. This is because new manifestations of corrupt execution errors occur all the time. And as such, automated routines may not be able to detect them when they first arise. The downside, quite clearly, is that human screening is much more expensive than automated screening, and it's also slower. This graph shows automatically reported CEEs in purple and human reported CEEs in green. Now, you may be able to see that automated reports are increasing over time. However, the authors state that it is unclear whether this represents an underlying change in the rate or whether CEEs are simply becoming more frequent, for example. The next trade-off that the authors propose to consider is post-deployment screening and pre-deployment screening. Pre-deployment screening is the simple practice which is already in place everywhere today, which is testing your CPUs before they are shipped to the customer. Post-deployment screening, on the other hand, is testing CPUs after you have already bought them, so while they are in use. Pre-deployment screening obviously is essential to detecting manufacturing defects, and as such is also essential to detecting mercurial cores. On top of that, however, the authors also state that pre-deployment screening is not as extensive as it could or should be for the reasons we got into earlier. CPUs are much more complex nowadays, so perhaps these pre-deployment tests need expanding. Post-deployment tests, on the other hand, are essential to detecting mercuriality. As we discussed, cores can become mercurial after lengths of time, so if you never test while they are in use, you may never detect that they are mercurial. Now, the underlying issue that the authors here wanted to discuss is that there's an inherent lack of interaction between pre- and post-deployment screening. The pre-deployment screening is done in isolation by the CPU manufacturers, whereas post-deployment screening is also done in isolation by the customers, say Google or Facebook. The authors propose establishing some sort of pipeline between post-deployment screening and pre-deployment screening to increase collaboration between the two and also allow mercurial cores to go from hyperscalers such as Google or Facebook back to the manufacturers so they are able to improve their tests and create more rigorous tests. The final two directions that the authors propose detection methods go is, for one, online and offline screening. Online screening is the simple practice of using spare cycles to verify the integrity of your computations, whereas offline screening is properly removing the machine entirely and testing it. The benefits here again lie at hand. Online screening is free, however, it is less intrusive. You're using the spare cycles of the core. As such, it's not as expensive as it could or maybe should be. On top of that, you're only screening one core at a time. Offline screening, on the other hand, is much more extensive. As such, you're able to, much more likely to catch all the errors that a machine may have. On top of that, as you're taking entire machines offline, you can screen multiple cores at once. All the cores of the machine can be screened, so this is another major benefit. However, it's expensive. You're taking the machine offline, this incurs a certain cost. The authors finally present infrastructure and application level screening. Infrastructure level screening involves detecting CEEs at an operating system level or some higher level, whereas applications level screening involves every program testing for CEEs in and of itself. Infrastructure level screening places much less of a burden on lower level program authors. It's much easier to write a program when you don't have to worry about CEEs, since that detection is done at a higher level. However, when CEEs do occur and they're caught at a higher level, you may not know where they occur, since you don't check every individual program, so you only know that it occurred, but you might not know where. Application level screening as such can allow you much more fine-tuned screening. And it also allows for some more specific mitigation techniques, which we will get into later. However, it's also more challenging to implement. There are some other approaches that the authors mention. For one, they mentioned that Google has an algorithm in place which checks whether multiple applications report issues from the same core. This core is then flagged, and they are then manually check it to see whether it is mercurial or whether simple bugs have occurred. Next, they suggest it would be possible to expand existing detection algorithms for reasons that are unrelated to mercurial cores, say for silent data errors or something like that. It would be possible to expand them to also include catching corrupt execution errors. Finally, the authors propose lockstep detection. This involves running the same program on two CPUs and then checking whether they agree. When they do agree, you know everything went right. When they disagree, you know an error occurred, and you can rerun the computation on a different set of CPUs, and you can then check whether one of those is mercurial. Now that we've looked at some methods to detect mercurial cores, let's look into how to mitigate their effects and how to deal with them when they do occur. The paper looks at two different directions. For one, we can deal with them in software, and we can also deal with CEs in hardware. However, the paper strongly advocates for software solutions for the simple reason primarily that it is much lower cost. If you were to fundamentally change the design of hardware to accommodate mercurial cores or to lessen the impact of mercurial cores, this would come at an incredible cost. Google and Facebook would be forced to replace their entire server fleets, and this might be incredibly expensive. On top of that, hardware and software solutions are much more flexible than hardware solutions, and they can be adapted much more easily than, say, a hardware solution. The paper does analyze some hardware design changes, though. However, these are mostly at a higher level and mostly aim at CEE detection or CEE prevention rather than mitigation. So let's look at software mitigation. Here, the aim is primarily to increase the tolerance of CEEs. When they do occur, you want to be able to deal with them, and you want to be able to deal with them in an efficient way that doesn't require you to recompute everything. For one, the authors propose checkpointing. This involves saving the state of your computation at multiple points, and if an error occurs, you revert to an earlier state and rerun the computation from that state on a different machine. Next, the authors propose triple modular redundancy. This involves running the same computation on 3 different sets of cores and then relying on majority voting to decide which is the final result. This incurs the obvious cost of doing the computation 3 times. However, the authors also suggest that this may not necessarily triple the cost, as some computations are already done twice for reasons unrelated to corrupt execution errors. Finally, the authors suggest code replication, which is similar to lockstep detection we mentioned earlier. This is simply replicating code to multiple cores and then running them simultaneously to check whether their results agree. The paper moves on to discuss hardware mitigation. The primary aim here being to reduce the likelihood of a CPU becoming mercurial. The first thing that the paper suggests is improving design for tests of CPU. This is the simple practice of making CPUs much easier to test once they have been deployed, meaning that Google and Facebook can more easily perform tests on their CPUs. Next, the paper suggests employing a more conservative design, which would favor reliability over performance. This, for obvious reasons, would make corrupt execution errors less likely, as each core itself would check for errors. Finally, the authors propose improving both CPU documentation and telemetry to make it much easier to figure out whether an error has occurred or whether the core is mercurial or whether a simple bug has occurred or something like that. Now, we've discussed software and hardware mitigation. However, there is also the possibility of simply trying to isolate cores once they have become mercurial. However, this is typically very challenging, and it's unclear whether this is even reasonably possible. However, the authors do propose that it may be possible to determine a certain set of instructions that can be computed safely on a certain mercurial core. If you remember, mercurial cores don't always cause issues for all types of instructions, so this may well be possible. However, this would require a much deeper understanding. Core isolation is a practice that is discussed in this paper, which was written in 2016. However, it is unclear whether this has found wider use. Then I would like to move on to the conclusion. The problem discussed in the paper was that cores silently produce errors and that go detected for varying lengths of time, mercurial cores. The aim of the paper was to raise awareness of mercurial cores and also as a call to action to both CPU manufacturers and owners of large server farms. The paper discusses a variety of detection methods for mercurial cores, as well as some software mitigation techniques. And it finally concludes that mercurial cores are a major issue that is going to get continually worse and desperately requires further research. Then I would like to move on to my brief analysis of the paper. As for some strengths, the paper identifies a new issue. It's one of the first to discuss mercurial cores. This is an obvious strength. It also looks at a variety of different approaches and keeps its options very broad, which I think speaks for the paper. On top of that, the application of it is very broad. CEs are not strictly related to hyperscalers. So this paper can be applied in a variety of different ways. It also discusses some future research directions, which we will get to in the discussion. As for some weaknesses, you may have noticed that there's an inherent lack of empirical data in the paper. The paper generally lacks results or insights or any sort of observations. It also strongly relies on an external study or a separate study done by Facebook. So when it does make empirical observations, it typically relies on this. Also, you may have noticed that there was only one graph throughout the entire presentation. This is the only figure in the whole paper. And it's unclear how this figure was obtained, and it's not really properly explained, nor is it really explained how they got the data for this. This is the paper by Facebook, which I was referencing, which deals with similar issues, however, primarily related to data corruption. Then I would like to move on to the discussion. And first, here are the future research opportunities that the paper presents for dealing with mercurial cores and corrupt execution errors. For one, they suggest creating fault injectors or generally trying to reproduce CEs, since reproducing them would allow us to study them in greater detail. They suggest some compiler optimizations, such as impact analysis, where a compiler would recognize code portions which are particularly vulnerable to CEs, or simply improving code replication techniques to only replicate key parts of code. And finally, they suggest, as mentioned, further expanding existing detection methods. Now, my first question to you is, which of these do you deem the most promising, or which of these would you most likely pursue?
The compiler analysis, probably.
And why that?
Yeah, it is more feasible compared to others, that's what I think.
I didn't quite understand that, I'm sorry.
I think it's more feasible to do that.
Yeah, okay. Anyone else? Yes?
Yeah, I would also choose
No worries. You can take this one.
just speaking to I think I would also choose compiler optimizations because it just seems much much less costly since it's basically just software. Whereas with the other two methods, it seems you have to actually mingle with the architectures or something.
But the compiler optimizations would involve replicating the code to multiple cores. So it would involve more cost when you're running the computation itself.
Oh, yeah.
Or would you?
Yeah, but I was thinking of like economical costs.
Yeah.
For like, but yeah, it would be less performant. That's true. Yeah.
Yes.
I would say that improving detection methods would be far greater for the future, because if we can detect more mercurial cores, we can also study them And I mean, we still don't understand them completely, and we will have to expand our detection anyways. So I think we should work on that.
Yeah.
I would also argue for improving detection methods, especially because if you start with this, you might then end up getting better compiler optimizations, because in order to, let's say, as long as it's very unclear on why they happen and how they happen, it's much harder to prevent them. And it would be beneficial to any method that solves them to know better why the problem arises.
Yes, that's true. Is there perhaps anyone who would advocate for fault injectors or improving CEE reproduction? Yeah.
I mean, I guess one argument for fault injectors is that while for improving detection methods, it seems you can just detect the errors better. With fault injectors, you can actually understand like how mercurial cores work and how it actually happens. So you can be much more preventive in building new processors.
Anyone else? Otherwise, here are some of my thoughts. I would strongly advocate for fault injectors and CE reproduction. However, I think they might be very challenging to implement before we properly understand the causes or are properly able to detect them. Personally, I think compiler optimizations may not be as much worth pursuing, since I feel like they're more avoid the issue rather than tackling the problem, which is preventing cores becoming mercurial. And expanding existing detection methods seems very reasonable, and it's probably the cheapest way to detect CEs. Anyone comments on this? Otherwise, I'll move on. The paper discusses a variety of software and hardware mitigations or mitigation techniques. And now I would like to know from you, which of these appear most promising and why? As a reminder, these are the various different methods. Which of these would you deem the most reasonable or the most promising?
I would probably say hardware mitigation because it allows software developers to basically ignore the problem, and this would
Any
be a big
specific
improvement.
technique, any specific method proposed for regarding hardware mitigation that you would?
No, I'm sorry.
All of them?
Yeah, it's just generally hardware mitigation.
And what do you think about the argument that hardware mitigation be very expensive to implement?
I think if we are all forced to implement software mitigation, it would increase like the cost of every single software development. So I think it would probably be come out the same, or I
So you
can't say which would
suggest
be
the
more
short, if I may, the
expensive.
short-term cost of replacing hardware is better than the long-term cost of running expensive computations, yes? Anyone else?
I just wanted to say that checkpointing is probably very difficult because sometimes you don't even know if error happens, right? So I wouldn't choose that one as a solution.
Not even in combination with maybe others, say combining checkpointing with code replication?
Yeah, then it might work because then you can verify if most of the cores did the same thing, then the one different is probably wrong. But just as a single point, it's probably impossible to implement.
Yes.
I would argue for improvements to CPU telemetry and documentation, simply because I think one of the main things that you pointed out multiple times is that it's not clear why they occur and how they occur. And as long as you don't know that, and it's a bit like, say, hand wavy on when it occurs, it's quite tough to solve the problem, right?
Yeah.
So that should, in my opinion, be the focus in general, to figure out why this problem occurs, and then you can solve it. But figuring out how to solve a problem where you're not sure when it occurs and how it occurs is pretty much unsolvable.
Yes, that's true. Any other comments on this? Would anyone like to advocate for triple modular redundancy? Or do you deem this not particularly reasonable? Okay. These are some of my thoughts. I think the triple modular redundancy appears the most promising if it can be implemented the way the authors suggest, namely being only replicating crucial code portions, since I think their argument that this may not necessarily triple the cost, or it makes sense to me. If it's already worth it to double the cost, what is rerunning it again once? I think checkpointing may be the best option for less critical code segments that are still important enough that errors shouldn't occur, but I think probably in combination with code replication. And improving CPU telemetry and documentation is a very simple measure that I think would go a very long way. Do you agree with this, or does anyone inherently disagree?
Thanks. Well, I think to triple basically all computations, as you said, perhaps it's not tripling the cost, but still, as you said before, like it's not resolving the issue, right? So I don't know if there's a way of writing programs that kind of verify themselves. Like if I'm looking for the solution of an equation, and at the end of the computation, I just plug it in again in the equation. Like I don't know, it's just like an idea. I don't know if it's really possible to do it on at scale, but yeah.
I think it would be possible. The authors briefly touch on this. I think this would be one of the methods that they mentioned regarding application level screening, if you remember that. That would be one such instance, I think. Anyone else? Then I'll move on. I briefly touched on some metrics that the authors presented. However, I don't feel like they're very extensive, and I think there's a variety of issues with them. First off, let's start easy. What are some metrics or some additional metrics that you may think of that we can use in relation to corrupt execution errors? And maybe what are some issues with the metrics here that you see?
Testing. Okay. I think the age metric is probably very difficult to calculate, because you would have to have a clock for each core, or just for how many cycles it computes something, and that's very difficult to take into account for a process, I think.
Yes. This is actually one of the challenges that the authors themselves also mentioned with their metrics.
I think a similar problem could be that the point where being mercurial is detected might not actually be the point where it happened, where the corruption happened.
Yeah.
So it could
Yes,
have been corrupted, and sometime later be detected, so the data might not even be that useful.
Yes.
It feels to me that the rate and nature of application visible corruptions is a pretty good way to measure how prevalent they actually are, because if your program is suffering from CEs, then if you want to minimize the amount of impact they have on actual real life executing code, you would want something similar to this kind of measurement of CEs. But that also means that you would not really be able to detect where they actually occur or on which cores. So that's also a downside of it.
Yeah, that's true. Did you have something or okay? Here are some of the downsides the authors themselves determined regarding their metrics. For one, they said that the fraction of cores exhibiting corrupt execution errors is very dependent on test coverage and on the resources you dedicate to testing. So if you test a lot, you will find more CEs. If you don't test at all, your fraction would be 0. Age until onset is mostly mostly dependent on how long you're willing to wait. If you wait forever, then eventually maybe all cores become mercurial. So who knows? And finally, rate and nature of application visible corruptions, they say, is more an inherent property of programs rather than a subject related to corrupt execution errors. Do you agree with these challenges, or can you perhaps find more? I think one personally that I have with the last point is it's not entirely clear to me how you would measure this, or I mean, like the propagation through programs and also the impact of the CE, it seems a little challenging to measure to me. Can you perhaps think of some additional metrics beyond these? Some other things that we may need to measure to properly help research mercurial cores or something like that? Anything else that isn't covered by these? I have a couple. For one, there is no consideration for the operational costs. It may be entirely possible that the expenses you make to detect mercurial cores and to mitigate their effects is more costly than just simply dealing with mercurial cores at all. So I think it would be very reasonable to have to somehow look at the operational cost of mercurial cores and the operational cost of dealing with them. False positive rate is fairly obvious. This is more in property of detection methods, but it would still be interesting to know. And then finally, the time or the detection time, which would be challenging to measure, but would also be very valuable to know. Do you have any further comments on this or any further metrics that you may propose? Yeah.
Could maybe a false negative rate be useful? Like for analogous reasons?
Yeah.
That's all.
Anyone else?
Maybe it would be interesting to know how long the average mercurial core stays in a system without being noticed, depending on the testing methodology and frequency.
Yes. So
to know how accurate we can assume our system to be.
So just so I understand properly, you mean the time between a core becoming mercurial and being detected, or?
Yeah, exactly.
Okay, yeah. Yes, this would probably be difficult to measure because you detect a mercurial core when it's detected, but.
Yeah, of course, but maybe like depending on the frequency we test, we can assume where on average how long it takes to detect one of the
Yeah,
mercurial cores.
yeah, that's true. Very good.
And then we can like give an accuracy of our system.
Yeah. Any further comments? Otherwise, I'll move on to what I think is the final question. The paper highlights a variety, or highlights the trade-off between reliability and performance. And now, what are maybe some factors that organizations should prioritize when making design changes? Or rather, what are some scenarios where you may favor reliability or you may favor performance?
One that immediately stands out to me is how critical the results of the computation are. So if it's a non-time critical computation, then the performance is much more important than reliability, I'd say, because you can just recompute.
Yeah.
And then on the other end, you have very critical operations that require exact results that aren't impacted by these errors. So I think that's something very important to keep in mind.
Yep.
Thanks. I think it also depends on where the processor will be used. Because, for example, if you're in a medical device or on an airplane and it does like, I don't know, 10 calculations per second, that's probably easy to do with 99.999 reliability. But if you're, I don't know, like on a personal computer where you're playing a video game, you probably don't mind if one pixel is off by something, but you want the millions of calculations to go somewhat decently enough, right? So yeah, it depends on where the system is used. Some systems probably want high performance and don't need high reliability, while others may need extremely high reliability.
Yes, very good. Any further comments? Yeah, here's some factors I wrote down. You mentioned the application requirements, so what the core is needed for. Also, I think you touched on this, the data sensitivity, or like how important the computation is, or how, or also like, yeah, just basically data sensitivity. If it's very sensitive data, you may favor reliability, or also in things related to security, you may favor reliability. And as for some scenarios that you could consider, you mentioned, well, I think it was you that mentioned health. This would also very clearly go in the reliability section, but for regarding performance, you have things like cloud services or real-time processing, that where you, or also genome sequencing, where you may favor performance since you want your results quick. Whereas in some topics like data storage or backup or finance and banking, or also communications, are some possible areas where you may favor reliability over performance. Does anyone have any final comments? Okay. Then that's it from my side. A big thank you to my mentors, Nisa and Ismail, for helping me cobble this together. And thank you for listening, and yeah, have a nice day.
That was a nice talk. Approaching to set up chat.
Haosung, are you online?
Yes, I'm online.
Okay. So
Yeah, should I
maybe-
introduce Pavel now?
yeah, maybe first Pavel can share his slides.
Mhm.
Yes, good. Okay, so Haosung, please introduce the presenter and then we can get started. Thank you.
Okay. So Pavel is currently pursuing a master's degree in MTEC, Master's of Science in Management, Technology, and Economics, and he holds a bachelor's degree from Bauman Moscow University. He is going to present RowPress amplifying radio disturbance in modern DRAM chips. Yeah, Pavel, please go ahead.
Can you hear me?
Yes, we can hear you.
Okay, thank you. So hi everyone, I'm Pavel. So today we're going to review and discuss paper on topic RowPress, amplifying read disturbance in modern DRAM chips. So here is the outline of the talk. Firstly, we will review the paper addressing questions: what is the problem the paper is trying to solve? And what are the key ideas of the paper, key insights? What are the key mechanisms? What is the implementation? What are the key results, key conclusions? And after that, we will go to the discussion part where we'll look at the trends, weaknesses, thoughts, ideas, and takeaways. So recent work by ETH scientists will be presented. And in this work, RowPress and new read disturbance phenomenon and real DRAM chips is demonstrated and analyzed. RowPress is shown to be different from RowHammer, and RowPress is demonstrated in real system, and also effective solutions to mitigate RowPress are provided. Here is the outline of the talk. Background information in DRAM will be started with. So DRAM is the prevalent technology for main memory. DRAM cell stores 1 bit of information in a leaky capacitor, and DRAM cells are organized into DRAM rows, as you can see on the slide. So read disturbance has significant system level implications because it breaks memory isolation. So a prominent example of this, RowHammer, where repeatedly activating and closing a DRAM row many times causes RowHammer bit flips. As you can see, when I'm opening and closing row 2, it's amplifying row 1 and row 3. So we call it the victim row. So RowHammer is the only studied read disturb effect, and various mitigations work by detecting high row activation count. So this raises the following questions. What if there is another read disturb phenomenon that does not rely on high activation count? It is found that RowPress is indeed such a phenomenon. So what is RowPress? RowPress is a read disturbance caused by keeping a DRAM row open for a long time, causing bit flips in adjacent rows. So these bit flips do not require many row activations. And scientists find that in some cases, only one row activation is enough. So now let's see some background and see how it's different from RowHammer. So instead of high activation count, RowPress increases the time that the aggressor stays open. So doing disturbs adjacent rows enough to cause bit flips without having very high activation count. So bit flips are observed even with only one activation in extreme cases. And now let us look at detailed characterization of RowPress. So the two most important takeaways from the characterization are: the first, RowPress significantly amplifies DRAM's vulnerability to read disturbance. And the second, RowPress has a different underlying failure mechanism from RowHammer. So now let us see how scientists come to this. And I will start with characterization methodology. FPGA-based DDR4 testing infrastructure developed from DRAM vendor was used to enable fine-grained control over DRAM commands, timing, and temperature for characterizing RowPress. A 164 DDR4 chips from all three major DRAM manufacturers are tested, covering differing densities and revisions. And the key metric being examining the minimum number of aggressor row activations in total needed to cause at least one bit flip, or we call it AC min. So a single-sided RowPress pattern is looked at where only one aggressor row is activated. So the time that the aggressor stays open or tag on from 36 nanoseconds to 30 milliseconds. And only what is necessary to understand the result that will be presented soon is covered here, and many more sensitivity studies are included in paper. So next, let us see the key characteristics of RowPress. So I have already showed two major takeaways. So now let's go to some details. So the first one, amplifying read disturbance in DRAM. So reduces the minimum number of row activation needed to induce a bit flip by just 1 and 2 orders of magnitude. So in extreme cases, as I already said, activating a row only once induces bit flips.
To write it such that it's
get worse as temperature increases. And different from RowHammer, affects in a different set of cells compared to RowHammer and retention failures, and it behaves differently as access pattern or temperature changes compared to RowHammer. So now let us see some details characterization results to understand how RowPress amplifies read disturbance. So first, let's look at how the minimum activation count to induce a bit flip or AC min changes as aggressor row on time increases. So AC min is shown on the y-axis and aggressor row on time on the x-axis, so both in log scale, and each data point show the average AC min across all tested rows, and the error band shows the minimum and maximum AC min values observed. And when when aggressor roll on time is 36 nanoseconds, the access pattern is identical to RowHammer. So aggressor roll on time increases, and the effect of RowPress start to become apparent. And two potential upper bounds of aggressor roll on time are highlighted, as indicated by JEDEC standard on the x-axis, which are the refresh interval and 9 times of that. So AC mean equals 1 is highlighted on the y-axis. So it is observed that as aggressor roll on time increases, AC mean significantly decreases, and in extreme cases, only one activation causes bit flips. So the same trend is observed for all other days tested for other manufacturers. It is observed that AC mean reduces by 21 times on average when aggressor roll on time increases from 36 nanoseconds to 70.2 microseconds for almost all chips tested from all 3 manufacturers. So when aggressor roll on time increases from 36 nanoseconds to 70.2 microseconds, AC mean reduces by 191 times on average. So it is concluded that RowPress significantly reduces the minimum activation count to induce a bit flip when aggressor roll on time increases. So next, scientists investigate how RowPress behaves at a high temperature. So 80 degrees Celsius, by looking at the AC mean, 80 degrees Celsius normalized to 50 degrees, which we show on the y side, y-axis. So it is observed that as aggressor roll on time increases, much fewer activations are required to induce bit flips at 80 degrees Celsius compared to 50 degrees Celsius. So it is concluded that RowPress gets worse as temperature increases. And now let us see in detail how RowPress differs from RowHammer. So the relationship between the cells vulnerable to RowPress versus RowHammer is first looked at the cells vulnerable to RowPress or RowHammer are defined as those that experience bit flips with the minimum activation count. So the overlap is then the number of cells vulnerable to both RowPress and RowHammer over the number of cells only vulnerable to RowPress, which is shown on the y-axis. So it is observed that as aggressor roll on time increases, only a minor amount of DRAM cells vulnerable to RowPress are also vulnerable to RowHammer. So most cells vulnerable to RowPress are not vulnerable to RowHammer. And the directionality of RowHammer and RowPress bit flips is also looked at. And it is found that they have opposite directions. Here you can see the graphs with a bit more details. Next, it is found that as aggressor row on time increases beyond a certain level, single-sided RowPress require fewer activation to induce bit flips compared to double-sided RowPress, which is very different for RowHammer, where double-sided is strictly more effective. So here again, we can see some graphs where data point below 0 means that fewer activations because of bit flips with single-sided RowPress compared to double-sided RowPress. So also it has already been shown that RowPress gets worse as temperature increase, which also is very different compared to RowHammer. So data point below 1 means fewer activations because bit flips on 80 degrees Celsius compared to 50 degrees Celsius. So now let's see the real system demonstration of RowPress. RowPress is demonstrated on real system with a recent Intel processor and Samsung DDR4 model with TRR RowHammer mitigation. And the key idea of the RowPress program is to keep a DRAM row open for a longer period by keeping access to different cache blocks in the row. So here is the key part of the program where the number of cache blocks read per aggressor row activation can be changed. And if only one cache block is read, so then the program does the same as RowHammer. Scientists run the program on 1,500 arbitrarily selected victim rows. And we show the total number of bit flips they observe on the left and the number of rows with bit flips on the right. So using a RowPress, the program will use bit flips when RowHammer cannot. So as we already said it previously. So now let's see how to mitigate RowPress. So methodology to adapt existing RowHammer mitigation to also mitigate RowPress is proposed. And the key idea is based on characterization results to first limit the maximum row open time to strike a balance between row buffer locality and RowPress vulnerability, and then configure the RowHammer mitigation to account for RowPress induced reduction in AC mean. But the evaluation of the proposed methodology on two RowHammer mitigation, Para and Graphene, show that they can be adapted to also mitigate RowPress at low additional performance overhead. The methodology is evaluated on two RowHammer mitigation, Graphene and Para, using RAMulator, and the additional performance overhead of the adapted mitigation over the original one in the key metrics being looked at. So key evaluation results show that RowPress can be mitigated with a low additional performance overhead. And for now, let's the talk to be concluded. So once again, in this work, RowPress, a widespread read disturbance phenomenon that causes bit flips in real DRAM chips is demonstrated and analyzed. RowPress is characterized using DRAM chips from all three major manufacturers, and it is found that first, RowPress greatly amplifies read disturbance by reducing the minimum activation count to cause bit flips by 1-2 orders of magnitude. And in extreme cases, only one activation causes bit flips. And the second, RowPress with a different mechanism compared to RowHammer. Also, RowPress is demonstrated in a real system with the user-level program, which induces bit flips when RowHammer cannot. And also, scientists provide effective solutions to RowPress with a low additional performance. So more results are found in the paper, and the work is fully open source and artifact evaluated. So for now, we can go to the discussion part where we'll look at the strengths, weaknesses, share some thought and ideas, and look at the takeaways. So as for strengths, this paper presents a comprehensive exploration of a previously identified read disturb phenomenon, RowPress, in DDR4 DRAM chips. So this investigation is significant, I think, in the context of system reliability, security, and safety. So the authors successfully demonstrate RowPress existence and its widespread prevalence across various DRAM manufacturers. So this contributed to a deeper understanding of memory isolation. So the first strand I can see at the paper meticulously characterized RowPress on real 164 DRAM chips encompassing all three major manufacturers. And this extensive empirical investigation showcases the universal applicability of RowPress and its amplifying impact as DRAM technology scales down. So differentiation between RowPress and other real disturbed phenomena such as RowHammer and retention failure is a significant contribution to this field. So the next one is observation from the paper directly. So observation one revealed that RowPress substantially reduces the minimum number of aggressor row activation as aggressor row on time increases. So this discovery is crucial as it highlights the vulnerability of DRAM to read disturb attacks under various conditions. So in extreme cases, RowPress can induce bit flips with just one aggressor row activation, which is a stark contrast to the conventional understanding of read disturbance. And what can we say about the next one? It's a thorough experimental methodology methodology employed in the experiments, including the FPGA-based DRAM testing infrastructure, exemplifies thoroughness and precision. So the deliberate measures taken to disable potential interference sources and ensure the absence of error correcting mechanisms at the architectural level contribute to the reliability of the findings. Also, I would like to share with you observation 5 and 6, that which highlighting the inverse relationship between tag on and AC mean, and are pivotal in understanding the intricacies of RowPress. So the ability to induce bit flips with exceedingly short tag on value underscore the potential of this read disturb phenomenon. So as a summary of the strengths, This paper aligns rigorous experimental methodology, the identification of new disturbed phenomena, and the exhaustive characterization of RowPress across a diverse range of DRAM chips. So these findings have substantial implication for system security and reliability, and they pave the way for further research in this crucial area of study. So what can I say about the weaknesses? So while the paper makes significant strides in covering and characterizing the RowPress phenomena, there are certain areas that warrant critical consideration. But the first one is a room for deeper theoretical analysis. Firstly, the paper primarily focuses on empirical observation and characterization. So while this is valuable in establishing the existing and impact of RowPress, so there is a room for deeper theoretical analysis. I think a more comprehensive theoretical framework would provide insights into the underlying electrical or physical mechanisms driving RowPress and enhancing our understanding of the read disturb phenomena. So also, I could say that we have a limited discussion on real exploits. So why it is not used in real attacks? Paper primarily addresses the impact of RowPress on DRAM chips and their vulnerability. However, in real world scenarios, we couldn't explore it in more detail. So exploring potential security threats or attack vectors associated with RowPress, I think would provide a more holistic view of its simplification. Also, as we already mentioned from the beginning, some deeper analysis of temperature effect also can be taken into account. So while the paper highlights that RowPress worsens as temperature increases, a deeper analysis of the underlying thermal mechanism and their impact on DRAM cells would enhance the robustness of the finding. So for now in the paper, we just analyzed two temperatures, and it is not clear is it linear or some other important finding we can find. So yeah, deeper analysis of temperature can find some interesting. And in conclusion, we just can say that there are opportunities for deeper theoretical analysis and more comprehensive exploration of potential exploits. So before I will go further, does anyone wants to add something regarding to weaknesses or strengths? I understand that the paper is quite difficult to understand maybe sometimes, but if you want to share your ideas, please move on. Okay, maybe for now I can move on, and later if someone will have something to add, just interrupt me. So as for thoughts and ideas, given the substantial contribution of this paper, it's worth considering how this research could be extended or applied in future work. So deeper exploration of RowPress mechanisms. So one avenue for future research could involve delving deeper into the underlying mechanism of RowPress. While the paper established, sorry. paper established its existence and impact. A more detailed examination of the physical and electrical process and play could provide a more granular understanding. So this might involve simulation of experiments and at the device level to uncover the precise interaction causing RowPress. So also investigation of additional countermeasures can be useful, considering alternative mitigation strategies or refining existing ones would lead to more effective protection against RowPress induced read disturbances. So additionally, investigating the potential trade-offs between mitigation techniques and system performance will be crucial in real-world application. Also, exploration, another interesting area for future research could be the exploration of RowPress and emerging memory technologies. So as new memory technologies continue to evolve, understanding the susceptibility to read disturbed phenomena like RowPress will be critical for ensuring their reliability and security. So the next one is, so the paper primarily focused on DDR4 DRAM chips, and extending this research to other generation of DRAM or even different memory technologies altogether could provide insights into how read disturbed phenomena evolve with changing technology landscapes. Furthermore, considering the potential implications of RowPress on memory isolation and system security is paramount. So future work could involve exploring potential attack scenarios that leverage RowPress as well as developing robust defense mechanisms to mitigate its impact. Lastly, conducting experiments in more diverse and extreme environmental conditions could yield additional insights. So this could involve testing under different, for example, temperature ranges, humidity levels, or even in the presence of other external factors that could influence real disturbed behavior. So in conclusion, this paper lays a solid foundation for understanding RowPress and in some implication for DRAM security and reliability. So further research in the suggestion direction could deepen our understanding and lead to more effective mitigation strategies. So as for takeaways, the paper convincingly demonstrated that RowPress exacerbates DRAM's susceptibility to read disturbed attacks, so potentially require only a single activation to induce a bit flip. Another takeaway is that the clear distinction between RowPress and RowHammer in terms of affected cells, behavior under temperature changes, and access patterns is noteworthy observation, underscoring the novelty of RowPress. Also, the proposed mitigation techniques, while requiring further evaluation, offer a potential avenue for addressing RowPress without imposing significant performance overhead. So also room for theoretical exploration. While the empirical observations are robust, deeper theoretical analysis could enhance our understanding of underlying mechanisms driving RowPress. The potential security threats or attack vectors associated with RowPress deserve additionally scrutiny to comprehensively assess its real-world impact. And temperature has a significant influence on RowPress, indicating the need for considering environmental conditions in future research. So actually, this is all what I wanted to share with you. And if you want to add something, get into takeaways, weaknesses, or ideas, of this topic, please share and we can discuss.
Any question from the audience? No one? Anyone? Okay, I think we don't have any question in the audience now. Oh,
Okay, thank you.
Just one question. Thank you. So you mentioned a couple times with weaknesses and your takeaways that there's room for theoretical exploration. How should that look in your opinion? I'm asking this because I guess we don't really have an understanding really of any of these facts, right? So how do you build that theory for any kind of exploration there?
I mean, there is an opportunity to understanding deeper physical processes of this observation. For now, we just observed that somehow adjacent rows are influenced, induced, but what exactly happened in a physical level, why it's happened, so it's not absorbed well for now. But if we will go deeper in the physical aspects, maybe it's a good idea to find something else.
Right, but what would going deeper in the physical aspects mean? Like how do you do that? Do you take a microscope and look at the transistors, or what do you do?
I mean, for example, we can measure some electrical aspects and understand how does it change during the experiments. Actually, I don't know. I'm not a physicist, but we didn't go. So scientists of this paper didn't go so deep into the physics of the processes. So do you think it's so doesn't make sense or it's impossible? So what's your idea?
Well, I'm certainly no physicist either. I was thinking perhaps a lot of this can work in simulation to some extent. I think there are some models out there, right, that try to basically, I don't know actually how low they go, if they go down to the atomic level, but they try to simulate, I guess, the real physical objects structure of the hardware. Perhaps RowPress can be studied further on these. Right? I'm not sure about if what the possibilities are to actually work at the electrical level. I guess there we need people who are experts, definitely not me. Thanks.
I just wanted to know if you have any idea why like if you actually have any idea why it is not used in any real attacks, because it seems like a very, like, let's say, advantageous vulnerability to use.
Actually, as I understand it, so it's quite really difficult to reproduce the real exploit, because you need to be a real security expert, because this phenomenon, RowPress, is just a way where you can go to construct real exploit. So it's the first, let's say, entry into the system which you are going to crack. And also, I feel that this phenomenon is quite fresh. So maybe some hacker experts need more time and resources to reproduce it. And yeah, so to conclude, it's just a way to go, but it's not explanation how to do it. So that's why you need say qualified people to really do it. And I think maybe it's a bit like a magic, or it should be very high qualified, because if you have an access to a random area of a DRAM, so, and you hope that attacking of one row could cause some let's say influence on the adjacent rows, which will be good for you. So it's like a lottery. So I think because of difficulties, that's why it's not real use in real world yet.
Yes, and I guess if you're like that qualified enough to do an attack like that, you wouldn't really usually be a criminal or something, because yeah.
Does it work? Oh, yes. Do you know how real the threat is for like actual users? Because what I understand is that you need to access very specific rows in order for it to like, so you're flipping bits in the rows next to the, so it's quite tough to get to like, how can you access the actual row, because memory is kind of abstracted from a systems perspective. So how realistic is the chance of an attacker actually finding the specific row that he needs to find for it to be a problem for the end user? So what I want to know is it actually a real threat to the user? Because it's very difficult to pull off, right?
Actually, it's a topic a bit different, but as I studied for myself regarding to RowHammer, so Google performed a real exploit, and they make it just given an access to very, very limited. So I would say that even if you have an access to some files or documents which are stored in a cloud, and you are somehow communicating with the memory. So actually, I could not give you some more details, but I feel that it's possible, but you need to be very, very qualified. But I don't know how in details. but it's real. Does anybody have other questions or comments?
I guess no, then.
Okay, so thank you. Thank you then.
Thanks a lot, Pavel. Haosung, do you have some concluding
Thank
remarks?
you.
Yeah, I think the presentation is okay. Although the in the discussion part, maybe it can be a bit better that Pavel stopped at each discussion points to give the audience some more time to think and maybe discuss a bit more. But yeah, I think overall it's not bad. Yeah.
Great, thank you, Haosung. So I'd like to make some announcement. At 6 p.m. you can access the quiz. You have only one day to answer the questions, so make sure that you do it as soon as possible. There are 2 evaluation forms on Moodle. One, you can use it to provide feedback to the presenter. And the other one is actually for the presenters, that they can provide feedback or they can evaluate the performance of their mentors. So make sure you attend those surveys. Thanks a lot and see you next week.